Morning, everyone. I'm Brendan Bradley, and it's my pleasure to introduce Pouya, as well as his co-authors, I think Charles and James as well, if I remember correctly, as well as a colleague from the UK, are going to be giving us a presentation this morning about some developments in light gauge steel construction, and hearing both about the general background for the topic and the need, as well as some of the impressive research developments over the last year. So with that, I'm happy to hand over to Pouya to start the presentation. And as always, please put your questions in the chat, and then there'll also be time for open Q&A at the end of the presentation as well.
Thank you. Thank you, Brandon. Hello, my name is Pouya Lotfi. I'm a PhD student at University of Auckland. The topic that I'm working on the topic that I'm working on in my PhD is about seismic behavior of cold-form steel strap brace stud walls as lateral force resisting systems for residential medium-rise buildings for New Zealand, under supervision of Dr. Charles Clifton from University of Auckland, Dr. James Lim from University of Waikato, and Dr. Iman Haji Rasuli from University of Sheffield. To give a general introduction about what is in general cold-form steel, because most of us are familiar with the hot-rolled steel, or so-called structural steel. Cold-form steel is essentially hot-rolled steel that is further processed in cold reduction materials at room temperature. So like the showed pictures, we have hot-rolled metal from one side, and then they get rolled, and the products would be cold roll or cold formed steel. And then the seam plates can get rolled and make some different type of profiles. Most of them have galvanized coating to protect from rotting and so on. And they are flexible in section geometry as well. Cold-form steel provide us with some advantages compared to timber or hot-rolled steel or concrete, which includes they are lightweight, non-combustible, they are termite borer-proof, they are easy and fast in constructions. We can have much work off-site, and they are dimensionally stable, durable, recyclable, and they are very good for computer control manufacturing and construction. In addition, in New Zealand, we have some national benefits because there are so many New Zealand roll forming machinery manufacturers and steel suppliers and related industries. Beside the cold-form steel, generally in big cities, not just in Auckland or Christchurch, in all big cities, we have, because of increased population and limited land availabilities, we need to go towards greater urban density, and most of the council encourage multi-story residential buildings. And because of mentioned positive points of cold-form steel could be a very good material for designing multi-story buildings to using its advantages. One of the most important part of the building is lateral force resisting system, which is the focus of this study. And lateral force resisting system for cold-form steel buildings is categorized between these groups. So we have sheathing with a steel sheet like this one's, sheathing with wood structural panel, plywood, plasterboard, or a strap braced like this one, and K-brace like these ones, and some moment resistant frames like this photo. In this study, we have studied some of these lateral force resisting system, but the main focus of this study is on strap brace walls. In this slide, I just give a very quick brief about what have been done in literature review. In the photos, there are some shaking table tests, mainly in North America, University of California, Illinois, this one Melbourne's, and University of Buffalo. They use different type of steel. Generally in Europe and North America, they use different profile of different grade and different thickness of steel. But as a general manner, they showed acceptable behavior and possible potential of such structures for multi-story buildings. For example, this test is a shaking table test on a 6-story buildings, which showed excellent behavior of light gauge steel multi-story buildings. Also, there are some other studies in Italy, Australia, and Canada. And as you can see, for example, this test is cyclic test. And as you can see, there is not a vertical load over them, which I will explain later. That one of the novelty of our work is that we wanted to do this cyclic test by applying vertical load. Beside a literature review and research have been done in other parts of the world, we have had some observations after Canterbury earthquake series of 2010 and 2011, in which the light gauge steel houses showed excellent behavior. The available houses in Christchurch was mostly 1 or 2 story buildings, but they behaved after Christchurch earthquake. They behaved very good, and they didn't show so much. They didn't need so much repairs, which we can see in the photos as mentioned. For this topic, actually, there are some challenges, general and local challenges. About general challenges, generally compared to timber and hot rolled steel, cold form steel is rather a new area, so studies on them is less, so we have less knowledge compared to other type of buildings. In addition, in this profiles, the behavior is complex nonlinear. Also, few experimental studies suitable for mid-rise buildings have been done. I mean that most of the studies did not apply vertical load during cyclic testing, so it's not suitable for mid-rise buildings. Also in New Zealand, we have some local challenges, including that in New Zealand we have different contexts. We have seismic issues and also different steel and profiles. Because of these two reasons, other studies from other parts of the world are not directly applicable to New Zealand. For example, the thickness, for example, North America and Europe mostly use low-grade steel with thicker plates, but in New Zealand we are using high-grade steel with thinner plates. Also, P21 test procedure, which is the conventional method in testing wall in New Zealand industry, is not suitable for mid-rise buildings. Based on the aforementioned information, at University of Auckland, we come up with a research program in order to develop a design guide for cold form steel multi-story buildings, which includes different phases, which is not just limited to my PhD, and next PhDs also work on them as well. So we scope in the 5 steps. The first step, understanding the behavior of cold form steel strap brace walls under corresponding vertical load of above stories, which actually could focus on the situation over there, and then as a second step, understanding the behavior of flooring system, ledger or platform, and interaction of two-story wall system and relevant detailings, which the focus of that part of a study would be the behavior of these systems and some numerical modeling to find the optimum solution, and then understanding the behavior on shaking table test at this actually system level, full scale structures. And then finally, providing the design guide for co-form steel multi-story building. So we have designed a novel test rig that enable us to apply constant vertical load during horizontal cyclic test, which is shown in this photo. You can see the 3D view of this test rig, which is suitable for phase 1 and also phase 2. That's in this test rig, we have the shown vertical load system that applied vertical load during cyclic test, and with these springs, we can keep these spring systems. We can keep the vertical load constant during cyclic test, and this is a view from the phase 2 test setup. Generally, this program could have some general benefits to industry, as that can enable co-form steel multi-story buildings, which could be an alternative solution for timber framings. So clients can choose between some options and grow the market shares for co-form steel buildings as well. Also to benefit from advantages of co-form steel in mid-rise constructions, so which is fast, economic, environment friendly, and durable. Also, by co-form steel, we have more off-site construction, so less inside activities and cost, and the more waste reduction and the safer workplace. Also, finding the optimum practical design methodology is another benefits of this research. Also, for New Zealand, we have some national benefits by presence of New Zealand roll forming machinery manufacturers and relevant industry. In this test program, we have some, actually, so far we have done 20 full-scale tests to study the effect of vertical load, investigation on different straps configurations and their pros and cons, effect of gypsum boards, plyboards, and do some study on different wall studs, depths, and base metal thickness, and investigate some innovative ideas. And the goal of this study is to provide, actually to end up with some wall design that provide higher ductility, meet the required drifts, and have better failure modes, have higher strengths and stiffness, and easier to construct. In this slide, you can see the 3D view of the test rig that has been designed and the photo from the test setup that is at the University of Auckland, the structural laboratory of University of Auckland, which you can see. This is the vertical load system, including load cell, jack, spring systems, and the actuators, the horizontal actuators, and the specimen sits in between the loading beams, like that. The specimens that we have been tested is stud walls, as shown in the photo. So they are light gauge steel stud walls with actually 2.4 by 2.4 meter walls. They have gusset plates at the corners and the straps, and some of them are K-braced, some of them different type of systems, but most of the specimens have straps, and the depth of the sections is some of them 89 to 150 millimeter, with the thickness of 0.95 or 1.15. The cords, studs, and top track, bottom track, and one nug at the middle. The straps is low-grade steels, G250, and with a thickness of 0.95. And the connections are based on screw connections with 10-gauge screws. Instrumentation of this test is actually as shown in this slide. So obviously we have actuator, horizontal actuator. So in the actuator there is load cell and LVDT, which measured horizontal load and displacements. We have load cell at the top for measuring the vertical load, strain gauges on the straps to measure strains, and LVDTs at the corner to measure any movements and any displacement of the corners of the walls. Load cell at this bottom to measure the hold downs load, and also draw wires to measure the displacement over the straps. In these slides, and to the next slides, I give a brief from results and conclusions, but the detailed results and conclusion will be released in upcoming papers. One of the results that actually we did in our test program was changing some detailing of the wall. The way of installing the nogging to the cores. Actually, at this area of the wall, conventionally we have this type of detailing, but changing this detailing to the detailing number 2, which is like that, we have a change in the hysteresis curves from red graph to the blue graph, which is actually considerable change, and we end up with better ductility and avoiding the brittle failure in the cords. So we used to have failure like this type of failure in the cord, but after changing this detailing, which is not very huge changing, is very easy change, we switched the failure from this part of the wall to the strap, which is desirable for us. Also in this study, we have studied K-brace system and compared them with the strap brace walls, which showed a huge difference between these two systems and showed that how desirable is the strap brace walls. So the red one is related to K-brace, the red graph is related to the K-brace, and the blue one is related to the normal strap ones, which showed the disadvantages of K-brace walls over strap brace walls, which is they are non-ductile behavior, and they showed that screw connections have very limited deformation capacity, and the wall showed low strength and stiffness, and shear failure of screws under combined vertical and lateral loads. We have observed them in very initial stages, and in general not acceptable behavior as shear wall panel in medium rise buildings. Also, we did a study between normal strap versus dog bone. From a structural point of view, maybe dog bone strap would be more desirable because we are sure that we don't have any tear out on the connections. But from construction point of view and practical point of view, normal strap would be much easier and cheaper to manufacture. And it is fine to have a screw at the middle parts. So it's more wanted by industry. So we did a study that it shows that with some proper detailing, we can have same behavior as equivalent dog bone straps. So the only point is that we need to have triangular pattern of screws at the connections. In that case, normal straps behaved very good, and we can also have a screw at the middle parts, which in dog bone we should not have screws at the middle part, but in the normal strap we can put some screws at the middle, which actually solve some sound and construction issues. Also, we did some comparison between different type of sheathing. with and without the straps. So some strapped and non-strapped wall with GIB system, Wilson wallboard system, which is a conventional method in New Zealand to board, actually sheathing the walls. We studied two systems, GBP, which one side plyboard and the other side brace line gypsum boards, and the other system GS2, both side standard gypsum boards. Actually, same as shown in the photos. And as you can see, for example, this is the tested wall that the gypsum boards have some crashed at the corners and the failed screws connections. As a brief of the results, sheathing provide higher initial stiffness than strap systems, but with less strength and ductility. So as a conclusions, only gypsum board system cannot be an acceptable system for mid-rise buildings because of low strength, brittle failure, and high degradation during the test. But plywood systems, the system that includes plywood, behave ductile and acceptable behavior till considerable drifts rather than only gypsum board systems. And the combined system actually behaved very well and great behavior, combining advantages of both systems. And as you can see in their hysteresis curve, the black one is the system have plywood and gypsum board. The red one is system just with the straps, and the blue one is the combined system, which is showed the combination of both together. Thank you for your attention.
Wonderful. Thanks, Pouya.
Thank you.